All right, honors geometry, your last set of notes for your honors geometry class. It's a statistics and probability day 6 notes on making decisions using probability. Now, this is not an easy topic. And again, I'm just touching on the topic. I'm not diving into it. So again, if you take a stats class, AP stats or regular stats your junior or senior year, you'll definitely dive more into this. But hopefully you'll remember this day and you'll have like a sneak peek at what you're going to see later on in that class. So when we do problems such as these, and we're going to look at significance tests, one with proportion and one with a difference of means, we do two types of problems. First is on what's called proportions. So a proportion is like a percentage, okay? It's your number of individuals out of the total. So say you're doing a survey, you want to know how many people like a certain movie, right? So you take all the number of people who said yes out of the total. It's just like a probability, right? Uh, we leave it as a decimal, but again, if you multiply it by 100, it would give you the percentage. The second type of question is a mean question. So now you have a bunch of values, right? So say you're measuring, how much cereal is being put into these boxes at a manufacturing plant, right? So you have all these measurements. You're going to add all the measurements together and then divide by the total. That gives you the mean measurement, okay? So in general, we want to find population values. These are called parameters that fit for everyone. So we want to know, in the entire United States, how many people, like whatever we're asking, okay, like this movie. However, it's nearly impossible to find your true population parameter. You can never survey everyone. It's impossible. You might not find somebody, they might not respond back to you if you send them something. So what we do is we make what are called inferences using sample data, okay? So once we gather our sample data, typically we use simulations, or to gather sample data, we use simulations and probability to make conclusions about the population, okay? And these simulations are imitations of chance behavior based on the model that accurately reflects the situation. So we get a sample, we use the given value to do some simulations, and then we use probability to make our conclusions. That's the process. Okay, so here's the statistical process broken down a little bit more. So first you state your question, right, about your chance process. Then you describe how you're going to imitate this chance process, right? How are you going to simulate this? Then you do many repetitions, which they're going to do that for you, right? They're going to do the plan and do for you. And then we need to do the conclude, right? This is your job to conclude, right? Use the results to answer the question. And again, this note is very, very, very important. Events that occur less than 5% of the time by chance alone provide convincing evidence, show significance. So the idea here is that if we get a sample value, right? We sample a group of people, we get that value. The question is, does that value show convincing evidence? Is it statistically significant, or could that value just happen by chance and not really mean anything to us? The example the AP stats teacher uses is a meteor hitting the earth versus someone dropping their calculator in the hallway, right? If someone drops their calculator in the hallway, you might look because it makes a noise, but no one's going to be like, oh, a calculator fell on the ground. No, because people do that all the time, right? They fumble, they think they put it in there. It just happens, right? So it's not significant. But say we look out the window and a meteor hit the Twinsburg Library, right? That doesn't happen every day. So we'd all stop, we'd look, we'd say, oh my goodness, right? That's significant. So that's the idea. We're looking for things that rarely happen, less than 5% of the time. All right, so let's see if we can go into Delta Math and do some of these problems. Now, this is the first type of problem. It's a proportion problem. So again, there are many different types you'll see. This is a rolling the dice. I would say rolling the dice and flipping a coin are very similar, okay? So it says Melanie rolled a die 40 times, and one of the 40 rolls came up as a 6. She wanted to see how likely a result of 1 6 in 40 rolls would be with a fair die. So Melanie used a computer simulation to see the proportion of 6s in 40 rolls, repeated 100 times. Based on the results of the simulation, what inference can Melanie make regarding the fairness of the die? So we have to think about a die, right? A die is usually 6-sided. So that means you have a 1 out of 6 chance of coming up a number, right? Well, this person did it 40 times and only 1/6. Their sample proportion, we call it p hat. Their p hat value is 1 out of 40, right? Well, if you divide 1 by 40, you get this decimal. So 1, sorry. So 1 divided by 40 is 0.025, right? So the question is, does this sample value provide convincing evidence that this die might not be fair, right? Maybe it doesn't land on sixes as much as it lands on the other numbers, right? That's the idea. We're judging the fairness of the coin. So what we do here is we look at the dot plot. The dot plot has 100 dots on it. These 100 dots are simulating 100 rolls. Sorry, is simulating rolling a die 40 times, and this is the proportion of sixes in those 40 rolls each. Okay. So now, I mean, 1 out of 6, if you do 1 divided by 6, it is, I believe, 0.167. 1 divided by 6. Yeah, 0.167, right? So that's the expected value. So notice where most of the dots are. They're in between 0.15 and 1.12. So that's about 0.167, right? That each of those dots represents, that proportion. So we're saying, okay, we think that 6 is unfairly not gotten. So we're looking at a proportion of 0.025 or less because, if it never showed up, that would give even more convincing evidence that the die is not fair. So now, once we identify our sample proportion and the direction we're going, typically it's less, we are going to go to our dot plot and we're going to find where 0.025 is. And 0.025 is right there. And we're going to circle all dots 0.025 or less. So in this simulation of 100 simulations, 100 times, 2 of them came out to be 0.025 or less. That's a probability of 0.02. That is less than 0.05. That means that we have significance. We have convincing evidence that this coin may not be fair because we're looking for rare instances. Rare instances are significant. They have convincing evidence. This is a rare instance. Okay, so how do we answer this question based off of all that pre-talk? Well, let's come down here. It says, since the simulation shows few cases, right, because it was 0.02, less than 0.05, of a sample proportion of 0.025 or less, we can conclude that the die is definitely fair. No. The die is likely fair. No. The die is quite possibly not fair. The die is not fair. The die's fairness cannot be determined. Our answer is going to be one of these two. Quite possibly not fair or is not fair. Now, in statistics, you need to learn that nothing is ever 100% definitive. So the die is not fair. That is pretty definitive. We don't know. We're just basing it off of this sample. So we're going to say the die is quite possibly not fair. And there we go. Okay, let's do one more of these proportion problems not involving a die or a. Here we go. Okay, let's do this one. Okay, it says the senior class president of a large university claimed that 25% of the senior class was interested in going on a senior trip. To test the claim, the senior class president conducted a survey of a random sample of 50 seniors, and 34 said they wanted to go on the senior trip. To better understand the significance of the survey, a simulation was devised based on the claim that 25% of seniors wanted to go on the trip. Each of the sample size 50 simulated 100 times. Explain how the results of the simulation can be used to support or refute the senior class president's claim. So what we're going to do here is we're going to look at the sample proportion, right? So the accepted value right now is 25%. Just 25% want to go on the senior trip. So when this person did a survey to find their p hat, out of 50 seniors, 34 wanted to go on the trip. That is a proportion of 0.68. So because that's more than 25%, I think we're trying to see, hey, should we raise this number, right? Do we think that more of the senior class want to go than just 25%? So I'm going to go 0.68 or more. So I'm going away. So because 0.68 is bigger than 25%, right, 0.25, I'm going to go more, greater. Okay. So now in this dot plot, we have 100 simulations, each dot representing asking 50 people, and this is the proportion of seniors that are interested in going. So there's 100 dots. So let me see where 0.68 is. So look at this. 0.68 is not even on our dot plot. It'd be over here. So look, there is 0% chance by chance alone out of these 100. So that's a proportion of 0. That 34 out of 50 would say they want to go on the trip. So this is definitely less than 0.05. So we definitely have convincing evidence that more than 25% probably want to go on this senior class trip. So let's see what we do here. So let's see how we answer this. So since the simulation shows few cases with a sample proportion of 0.68 or more or greater. So the claim that 25% of the senior class wants to go on the senior trip is definitely true, quite reasonable, likely not true, not true. So it's probably likely not true, right? It's probably more than 25%. And there we go. All right, let me see if I can find one where it's going to be the other way, where it's going to be greater than 5%. Let's see. All right, let's try this one. Okay, so it says there is an upcoming election for student council president at a high school. Candidate A must get over 50% of the vote to be elected. A poll was taken of a random sample of 50 students from the high school, and 27 said they would vote for candidate A. Simulations were done with a population percentage of 50% and a sample of size 50 to see how likely a sample of 50 would have 27 who preferred candidate A. The results of 100 simulations are shown. What conclusion can be drawn regarding the likelihood that candidate A will win the election with more than 50% of the vote? So let's take a look here. So in our sample, P hat, of the 50 students we sampled, 27 said that they would vote for candidate A. That is a proportion of 0.54. So because that's greater than 50%, we're going to look for how often does that occur by chance, okay, 0.54 or more, all right? So if I look at the dot plot, 100 dots, because there were 100 simulations. So 0.54 would be right here. So I'm going to go 0.54 or more. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 5, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. 36 out of the 100 simulations came out with a proportion of 0.54 more. That's 0.36, which is way more than 0.05. So this result can just happen. It can just happen way too often for it to give any convincing evidence. So this is where we're going to answer sort of the other way. Let's see what our choices are. So the simulation shows that many cases with a sample proportion of 0.54 or more. Therefore, the results of the survey are inconclusive, indicate candidate A will definitely win, will most likely win, will most likely lose, will definitely lose. We're going to say are inconclusive. They do not provide convincing evidence, so we can say nothing. And there we go. Okay, so I'm going to stop the video now. We'll do the means, the difference of means in the next one. So again, I guess I lied. This is the last lesson, not the last video. Sorry.